So here's the problem from this week. It's from this year, January, and yeah, you probably have read the problem maybe, but as a summary, we have an n by n grid of cells where n is less than or equal to 1,000, and we're putting cows into some subset of these cells. There's only one possible cow for each cell, and we're also given this condition that every subgrid of 2 by 2 is going to contain exactly 2 cows. So for example, if we look at this 2 by 2 has these 2 C's, and the dots are like no cow. And then this one also has 2, this one has 2, and this one has 2. Okay. Yeah, and if we look at this one, this subgrid has only 1 cow, so this one doesn't work. And this is the only restriction we have. So after that, given that like each cow in a position has a certain, what is it called? I don't know. It says the total beauty. Okay, so like each cow contributes some number to the total beauty of a picture. And we're trying to maximize the total beauty of all the cows that we use. So yeah, there's an example here. And I think when you first look at this problem, one of the ideas that you could think of is using some sort of algorithm like dynamic programming, which I think Vivian talked about before, because DP is usually for like maximizing or optimizing something. And if we could kind of like build a grid up from the small one to like the full one that we have, then we could possibly try to maximize the total beauty of the photo. But yeah, this isn't the official solution, and also I think there is a DP solution, but I don't really know what it is. So yeah. And given that this problem is from silver, it's probably not going to require DP as the solution. So the kind of problem that this actually is called an ad hoc problem. And basically what that means is that it doesn't really have a category. So we had like a prefix sums problem and then one that used 2 pointers. But this one doesn't really have a specific algorithm or strategy that you can use to just solve it. And I think these types of problems usually appear more in bronze than silver because silver is about these like different algorithms. But as you can see, it did show up. So that's why I'm doing this problem. So for these types of problems, what's really helpful is observations. And pretty much anything that you observe that you might think could be helpful at all, you should kind of take note of because that might end up being the solution. And also what you want to do is look at the problem from different perspectives. Because there is no specific like strategy that you could use to solve such a problem, if you look at it from a different like angle, it could help you find a solution. So yeah, if we try some observations and basically just see like what could happen in this, like given this constraint. So first of all, I think this constraint is like relatively restrictive. Like this configuration is very nice. There's like a bunch of patterns. This is all the same. This row is all the same, and this row is all the same, which could lead you to believe that like there's some kind of thing that's going to have to be true for all possible configurations that satisfy this property. So yeah, if we just, let's say we have like two cows or two not cows, like two dots next to each other, we're basically just going to be looking at like some cases. So if we have two cows next to each other, then these spaces like under the two cows have to both be dots because this subgrid has to have exactly two cows. And then if we look at the next subgrid, we have to have two cows. And then this goes on, two dots, two cows, and so on. And this applies for like going up. So both of these directions, they alternate between two cows and two dots. So now we look at what happens in these different directions. So if we place another cow next to this first row cow, then this one has to be a dot, and then so on. And it alternates again. But otherwise, we could have a dot here, and then a cow, and then a dot, and then a cow. Like this is all just following the restriction. So like this has to have exactly two cows, this one, and so on. So yeah, I think when you're listing these out, it's pretty easy to see that the first thing that we did was if we place a cow next to this one, it has to be C dot, and so on. And if we don't, then it has to be dot C, and so on. So these are the two cases. And in both of them, we have these columns alternating. And this goes for this direction too. So yeah, if we look at the case where we're having a cow and a dot next to each other, for this second row, well, we could have a cow and a dot again, in which case this would just be the same as the first configuration rotated by 90 degrees. So instead of, like, basically the would have, if we look at this, two cows, if we look at this, also two cows. So we need these like alternating rows instead of alternating columns. And then we just do the rest same as before for this direction and this direction. Otherwise, we could have a cow and a dot like before, but instead of doing a cow and a dot underneath those, we do a dot and a cow. So yeah, now there's kind of a bit more freedom to what we can do, because whenever we have two cows or two dots next to each other, we have a lot of things that are fixed. Like we had these two cows and then everything else in this direction and this direction is fixed. But if we had this like subunit, then we can basically try and see what happens for the others. So if we do like this, then we're going to either go this way or this way. And basically what you end up seeing is that we can either like start a new subunit like this, where the two dots are diagonal from each other and the two cows are diagonal from each other, or we start one of these, where we have two cows and two dots next to each other. But in both cases, what we're creating is alternating rows or columns. So you can probably see now that like the recurring idea is that we usually either have alternating rows or columns. And we did that with like casework, I guess, or just kind of seeing what works. And if you want a formal proof for this, we can just do proof by contradiction. So if we assume that the rows and columns, or not all the rows or also not all the columns alternate, then we're going to have two cows or two not cows in a row or in a column next to each other, because if we don't, then everything is just alternating. And that's contrary to what we claimed. So we know we have this or this at some point. These are symmetric, so if we just consider two cows next to each other, then we have this configuration which we started with. And now we can see that everything here on out and here have to be alternating from what we did before. This is just if you want to like make a solid proof that this is true. Yeah. So now that we have this like claim, it's actually not too bad because first of all, n is pretty small. It's only 1,000. Oops. Yeah, n is 1,000, which means we can afford O of n squared. And we can get this by, we either have all of the rows or all of the columns alternating, so we can consider two cases. They're pretty much the same, but we're either going through the rows or the columns alternating. So if the rows alternate, then we're just going to go through all of the rows and like this row, this row, this row. And we know they alternate, which means we either go starting from index 0 and then 2 and then 4 and so on, or we take 1, 3, 5. Like we put cows in the even ones or the odd ones. And you can just add these up, the like beauty values, I guess, into two values and then take the maximum for each row. You add the maximum up for each of the rows. Taking these sums is O of n, and then there's n rows. So this is O of n squared. And then same thing for the columns. So in total, if we check both rows alternating and columns alternating, then we have O of n squared, which is enough to pass. Yeah, so I don't really remember when we started, but because this problem was like, I think once you find the observation, it's really not hard. I was just going to show one other ad hoc problem. I can go through it quickly if we don't have time, but basically if we summarize this, we have this n by n grid, and then a cow or a painter is drawing a bunch of different rectangles and basically painting over whatever was there before with different colors. So we have 1 through 9. And we're asked how many of the colors that are on the canvas that you can see could have been the first thing that was painted. So n is pretty small, it's only 10. And yeah, we're just gonna try to find which colors can be painted first. So for this one, I like the actual solution was more intuitive for me. But if you think about two rectangles that overlap, obviously only one of them could have been painted first. So we want as little or as few overlaps as possible, which means that we're just going to assume the smallest possible rectangle for each color. Like basically what this means is if we look at these twos, there's 4 of them, the smallest possible rectangle that could have been painted of twos was this. But you see that like this was actually what was painted, but we don't really care about that. Yeah, so if we just assume like the smallest possible borders for all of these colors, then we can look at which ones are never covering another rectangle. Like what this means is like you see this 3 or these 3s cover the 7s, which means they couldn't have possibly been painted first. Another way to say like covers is like the 3s are inside the 7s rectangle. So yeah, we see that the 3s are in the 7s, which means 3 is after 7. And the 7s here are in the 2s, which means that 7 is after 2. So the only thing that could have been first is 2. Yeah, so we were pretty much only caring about the overlaps because if they don't overlap with something, then they obviously could have been painted first. So if we go through each possible pair of 2 rectangles or 2 colors, and then see if they overlap, then does one of them go into the other's rectangle? And for each possible color, if it never goes into another color's rectangle, that means that it could have been painted first. So yeah, that's the idea. I think if you look at this picture long enough, you can probably see something similar to that. It might be phrased differently in your head, but that's the idea for this problem. So yeah, that's my talk on ad hoc problems. I hope it helps. That's it.